In this video, we're going to find a technique for determining whether a point is in the image of L. And the context we're going to use this in is a linear map that maps from R2 as our input space, and it's going to output into R3. And we're going to consider the point -6, 2, 10 as a starting point. So -6x, 2y, so some point in space, -6, 2, 10. And the question is that point in the image of the transform given here? Well, what does that mean again? It means that there is some x and y. If it is in the image, then there is some x and y that maps to the specific coordinates -6, 2, 10. And so our challenge is basically to reverse engineer that x and y. If we can find that x and y, then we know that the point we've been given is in the image. But notice again, the image is about the output space. And being in the image means there's an input that leads to that output value. So let's just frame that. Our goal is to find an x and y input that's going to go into our transform. And we want it to satisfy the condition or such that the L of xy is specifically equal to -6 to 10. Well, this sounds like we're setting up a system of equations, so let's make that concrete. L of xy, if we format this in column form rather than row form, I think it'll make it a bit easier to follow. The first component of the output of L of xy is just 2x minus 3y, exactly what's given in the function. The second output is x plus y, and the last output is 4x plus 5y. So if we transform any element of xy through this transform, we get this three component output back. We want that to equal the target value, the -6 to 10. We've worked with enough linear systems now, though, to recognize that we can solve this with the extended matrix form. We only need the coefficients, the 2, the -3, 1, 1, 4, and 5. And the right-hand side of our equation is the -6, 2, 10. If we can solve this, that's the same as solving this. That's the same as finding x and y that satisfy our criteria. So now we can proceed to row operations on this and see what we get. I really like row 2. It's nice and simple, has lots of 1s in it. So let's just keep R2, and that'll be our 1, 1, and 2 value. The next thing I want to do, I think, is cancel out these two and get a leading 0. So if I take the first row minus 2 times the second row, so row 1 minus 2 row 2s, that's going to give us 2 minus 2 is 0. I'm just going to do them all here. 2 minus 3 minus 2 more is -5. Okay. 0 minus 5. Then row 1 minus 6 minus 2 more of these is actually -10. So we get that. And we need to get one more row down here. Toss up how we do that. I'm tempted to take row 1 and row 3. If we take 2 row 1s, we'll get a 4, and then we subtract that. So let's try 2 row 1s minus row 3. I know it's a lot of row 1s, 2s, 3s with multipliers of 2s, so we got to be careful with our mental algebra, but here we go. 2 of this minus 4 is 0. That's the point. That's why we set up that choice. 2 of these is -6, minus another 5 is -11. And then 2 of these minus 12, minus 10 more is -22. Perfect. Now we see these two rows here are pretty similar, so let's just keep row 2 the way it is, which is 1, 1, 2. We're going to take the row, it's row 1 now. We're going to take the second row here and just divide it by -5. So row 2 divided by -5, that's going to give us 0, 1, 2. And 11 times this, whatever. These are the same row, just scalar multiples of each other. So we're going to get a row of 0, 0, 0 when we cancel those. And last but not least, we can take our row 1 minus row 2. And that's going to give us 1, 0, 0, 0, 1, 2. Keep row 2, and keep row 3 the same as well. And there we have our solution to our equation. This is giving us an x value of 0 and a y value of 2. So it makes sense to confirm this. Let's do that on the next page. Just pasting in the actual function for easy use here, we can confirm or check that L of 0, 2, well, that's equal to 0 minus 3 times 2 is -6, 0 plus 2 is 2, and 0 plus, hey, that's 0 plus 2 Negative 6, 2, 10 is our point, which is perfect. So what does that tell us? Again, we had the specific question about image. It tells us that negative 6, 2, 10 is an element of the image of L. Going back to the previous slide for a moment, it can be reached. This is a point in the output that can be reached from a certain specific input, and that input in this case is 0, 2, and we've got a nice confirmation there. Now that example shows nicely how the question about an image point, whether a point is in the image or not, boils down to a system of linear equations. I'd like to take it one step further though, and I think that's going to be easier to illustrate if we take a look at the function again and ask now about a point that's not in the image. So what does it mean to not be in the image? Well, let's set up the same system of equations. The goal is the same. In principle, we want to find, I guess the change is find if xy exists such that the transform of those x and y values is equal to now 1, 2, 3. Well, that's the same as asking if I transform some L of xy. I know I'm going to get the same thing we said before, 2x minus 3y, x plus y, 4x plus 5y. I want the output of that to equal the specific target value that we've been given, the 1, 2, 3. And these values here just came from the description of the actual transform. So 1, 2, 3 is now our target. And we know that that's equivalent to the extended matrix form of 2, negative 3, 1, 1, 4, 5, and 1, 2, 3. So our question now is, can we solve the system of equations to find the x and y that make this output value? In this case, it's not obvious to us, but the question was phrased in a way that we think it's not possible, but let's see it in action. Let's imagine how we're going to do this transform. Well, I'm going to take row 2, because again, it has 1, 1, that's nice and simple, 1, 1, 2. And how else are we going to do this? Oh, wait, all of our row operations depend on the left-hand side, really. So I'm going to do exactly the same row operations, and the only thing that's going to change is what happened on the right-hand side. So let's play with that quickly. We're going to take row 1 minus 2 row 2s, and that'll give us a 0 in the first slot. So row 1 minus 2 row 2s. That's going to give us a 0, and then row 1 minus 2 of these is minus 5. Then row 1 minus 2 of these is going to be 5. No, sorry, let's get that right. This minus 2 of these is minus 3. And to compute the last row that we're missing here, we're going to go back and again, our choice, but I'm going to do the same thing I did last time. Take 2 row 1s minus row 3. 2 row 1s minus row 3 to get a leading 0. 2 row 1s is minus 6. Minus row 3 is minus 11. So we see exactly the same left-hand side here. Just going to make a little more room for our extended matrix structure here. There we go. And what has changed are the right-hand side values. So if we go over to the last column, 2 row 1 is 2, minus row 3 is 3, so minus 2, so 2 minus 3, sorry, is negative 1. And we can just tidy that up. We can already see there's going to be a problem. These last 2 rows here are not mutually compatible. But let's play it through just to make that crystal clear. We're going to keep the same first row again. We can take the second row and divide by negative 5. That'll give us 3/5. And if we take the third row and divide it by negative 11, we're going to get this. And this gives us the realization that y has to equal 3/5 from the second row. Let's put that beside second row. And we also would need at the same time that y equals 1/11, and that is impossible. And that means that there's no solution. And that means that no xy value pair exists such that L of xy is going to equal our target value 1, 2, 3. And so 1, 2, 3 is not in the image of L. And that's fine for what it is. However, I'd like to take advantage of this moment to think about those parallel solving processes we went through and tie that back to the ideas of linear transformation, span, and things like that. So if we ask the question, is the point ABC in the image of L. And that's what we did for the last two examples. What we end up doing is creating a system of linear equations based on the transform for the left-hand side and our point on the right-hand side. That's fine. But then when we built our linear system, what we ended up with was effectively asking this question here. Take the coefficients that go with x, take the coefficients that go with y, these are the coefficients in our linear system, and put in our point here, our target point. And when we write it out like this, we can see what we have are two building block vectors, which I can take linear combinations of. The linear transformation does this linear combination for us by we set x and y, we can get any multiple of these two building block vectors, and asking whether that linear combination gives us our target value. And that means that we have an equivalent question for this transform here. Is ABC in the image of L is exactly the same question as is ABC in the span of a set, and specifically the span of these two vectors given by the linear transform. So 2, 1, 4 here, and negative 3, 1, 5. So all of a sudden we have three relationships going on behind this image question. Does a point belong to the image? Well, it does if it's a solution to a linear system of equations. If the solution exists, then the point ABC is in the image. Or we can phrase it as, is the point we are interested in the span of these building blocks for the image? And now we can start thinking of, well, maybe the image, we know it's a linear subspace, and now we have two vectors that span it. Well, that sounds like basis territory, so we'll explore that next.